hello, everyone. A slightly fuller class day, which is interesting because it's a review day. Usually I get less people on those days. But glad to see you all. So, I think it's fairly clear, but just to make sure it's very clear. The multiple choice is this Wednesday, 2 days from today. So today is the 25th. So your all's free or multiple choice is this Wednesday, the 27th. And then the free response is this Friday, the 29th. Exact same structure as last time. 50 minutes for both during the class time. The multiple choice, the Scantron will be on the back paper. I'm going to double check before I tell you all another thing. So I've got all the tests here. How exciting. Alright, so let's see. Did I do a good job? I did! To make things more streamlined, so the test, the first page, it's 20 questions, multiple choice. I have actually included the scratch paper as one of the stapled on papers. So it makes your life hopefully a little easier. So when you get the test, you won't have to worry about passing out scratch paper or anything. Literally, you'll just tear off the back 2 pages. One is the Scantron, one is the blank paper. The equations are all on the bottom. Same old, same old. And then you have 50 minutes to kind of get it done. Very straightforward. Just remember, make certain you put your name and your PID. We pretty much did a great job with that last time. Made my grading way easier. Because the problem is, if you do not put your UCF ID correctly, that is what I use to match. So I open up a big Excel file. I have a spreadsheet. I pull all the people from the gradebook over with their IDs. I download the document with all the grades on this. If your PID doesn't match exactly, I have a very fun time of figuring out which test is yours. Which is a whole, just takes a bunch of extra time, delays things. So just be careful on that. We try to check them when you turn them in. I think I only had like 3 people out of 200 that I had to kind of fiddle with. If that happens, it just means that I could potentially miss your test. I will have it. I do not lose my pro tip for you all, the way you don't lose anything, is not to throw away anything. So every single paper that I collect does not get thrown away. And that's how I guarantee that I don't throw away one's test or anything like that. So anyway, didn't have any problems last time, don't expect any problems this time. Make certain you bring a calculator. Make certain your calculator is charged beforehand. Like last time, I will raid my high school classroom for the calculators I have, and I will bring them here, so if for whatever reason yours is dead or whatever, I will have one. I cannot promise I'll have enough, depending on how I do forget theirs. I also, you've probably already experienced this, hopefully you've built a nice relationship with your calculator. Your calculator is something you're going to be using a lot, and you get hopefully very comfortable with using your calculator. So when you have to use someone else's calculator, it just throws a wrench in things. It's not ideal for you. So double, triple check batteries and that you bring it. So on the test day, note card, ID, calculator. I'll send out an announcement to remind you all. I get it. People forget. I forget. These things happen. But that's my reminder to you all. Okay. Any questions logistics-wise or anything before I kind of get into more review? All right. So today I'm just going to be kind of doing a variety of problems. So last class I posted, or we went through and we kind of made an outline. Here are all the things you need to know. I posted that last week in the Files tab in the Test 2 thing. So if you didn't know that was there, it's there. Test 2, review. So let's just quickly skim through this, remind you all of the really, really important things that if you haven't looked them over. So, first we start with work and kinetic energy. You need to know what work is, that it's FD cosine theta. That the sine of work comes from the angle. And what is work? It's whether you gain or lose energy. If you gain energy, you'll end up getting a positive answer. If you lose energy, you'll end up getting negative. The math tells you it's a scalar. Kinetic energy is 1 half mv squared, very straightforward. Conservation of energy is a very, 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 very important thing you all need to know. This is a critical concept for like, not just this class, but in general. This is one of those, it is so useful. That energy is conserved. The energy I start with is the energy I end with. Tacking on, and so make certain you all can, we'll at least do one example of that today. Make certain you can set up conservation of energy. If you cannot solve a conservation of energy problem by the end of this class, I have failed you. Or you can have just, I don't know, some combination of something is really wrong there, because this is like the bread and butter of a huge piece of this class, is being able to do conservation of energy. The little bit extra that gets tacked on is if energy is gained or lost. So energy is conserved, that is true. Within a system, within the entire universe, energy is always conserved. But within a piece of the universe, you can add or lose energy. Easy example of that, your car. Your car is sitting in the parking lot, if you have it here, hopefully not moving. The second you hit the gas, it starts moving. Technically that gas was in your car, whatever, but it gained some kinetic energy. Where did that come from? The gas, whatever. The work was done. My energy changed. So, make certain you all can do this whole work equals the change in energy. Long story short, did you get, and this kind of boils down to the initial energy plus work equals energy final. If you gained work, you have more final energy. Sorry, if you gained energy, work is positive, your final energy is higher. If you lost energy, your final energy is lower. Friction, again, that comes from the math. You'll find that friction is always going to be negative. Friction always takes away energy. And then, yeah, power is just kind of chucked down here. Make certain you remember power equals work divided by time. Power is literally defined as energy gained or lost per second. Work divided by time. Energy gained or lost per second. So, make certain you can do conservation of energy. Make certain you can do momentum. Momentum, we're back to vectors. Yay! We'll do an example of those today. There's three cases: elastic, inelastic, and separation. Remember, these are vectors. It's in all bold, all caps. You have to break them into X and Y. If the problem gives you a momentum of a car is going north and another car is going east, that is an X and Y. You have two equations to set up. You have to set it up in X and Y. If they are not parallel to each other, you have to set up two equations for this. One for X, one for Y. I will not give you a problem. I will not give you an elastic collision problem. So elastic, they bounce off each other. I will not give you one of those where there's two unknowns. Okay? So elastic collisions, energy is conserved. So one of the possible problems, and I told you all this, and I told you it's a bunch of math and stuff like that. In elastic collisions, you can set up an elastic collision momentum and a conservation of energy. You got two equations, two unknowns, and it's a bunch of math. I will not give you one where you have to do that much math. I've told you all this many times. If you know what you're doing physics-wise, set like the max. If you know what you're doing physics-wise, 75% of your time at 75% of the time is setting up the problem. At most, 25% of the time is the math. If you know what you're doing. Obviously, it can take longer one way or the other if you're not sure what you're doing. But I will never give you a problem where if you know what you're doing completely, that you're spending most of your time just doing a bunch of algebra. That's a waste of time. I'm not testing your algebra skills. I'm testing your physics skills. And so 75 to 80% of your time should be setting up the problems. 20 to 25% of the time is the math. Okay? So that's a good rule of thumb when you're going through these problem sets. You're like, this is a lot of math. This is taking me a lot of time. I'm not going to give you one that takes that much time math-wise. All right. Cool. Impulse. Change of momentum equals force times time. May or may not look at one today. Universal gravity. Fg equals g, m1, m2 over r squared. If they're going in a circle, you can set that equal to mv squared over r. Remember that. Do some things. And then when it comes to oscillators, it's kind of half definitions. Actually, it's mostly definitions. Do you know what frequency is? Do you know what angular frequency is? Do you know what period is? Then the equations are just kind of all there. Can you do math? Once you know what the variables are, the equations aren't bad. But you do need to know the equation for an oscillator, which is just A cosine omega t. A is the amplitude, omega is the angular. Well, that's spelled some way. Did I do good? All right, great. So let's go ahead and and then again, just a bunch. When it comes to the oscillator stuff, do you know what the variables mean? And then there's an equation for a pendulum and an equation for a spring, but those are it's just math. There's nothing too fancy there conceptually. Conceptually, this is the part that's in the equation for the oscillator. All right, let's do some math. So I'll kind of just tack this on to the end. So let's start with the first thing I said was super important, which is conservation of energy. And I'm just going to make up a problem. These problems are so easy to make. Because they all boil down to what energy do I start with, what energy do I end with, set it up, do some math. Okay, so a spring, a horizontal spring is located 5 meters above ground. If I compress the spring to 0.5 meters and it has a spring constant of 1,000 newtons per meter, how fast will the object go right before hitting the ground? So the wording here is not the most eloquent, but go ahead. Read it, think through it. These problems boil down to. So first off, you have to recognize it's a conservation energy problem. I kind of told you all that. How do you realize that? At the beginning and an end. The reality is, when there's a beginning and an end, you start above ground, you end below ground, or there's a spring. All those are like key words for conservation of energy. Conservation of energy is, and there's no collisions. Nothing is colliding. There's a beginning and an end. My height is changing. There's a spring involved. Oh, you need one more thing. If I compress a 10 kilogram box. Okay, not the most eloquent. But it gets the point across. I spend a lot more time thinking about the wording on your test, so don't worry that it's going to be this. So it's always handy to draw. And if I don't clarify otherwise, assume no air resistance. This is a good rule of thumb. If you don't see the word air, assume no air. That's just a good rule to kind of have somewhere in the back of your mind. Slash friction. So, we draw a pretty picture. We have our spring, it's horizontal, my box is compressed, I'm 5 meters up, and then at some point later, spring still exists, my box is now about to hit the floor. Oh, what a pretty picture. All right, I'm not actually going to numerically solve this because the reality is, so this type of problem has enough steps involved that it would be kind of more in the free response category. Yeah?
Would we have to use kinematics?
Would
we have to use kinematics?
You may be able to do this with kinematics, but anytime you see a spring being compressed, it's a good conservation energy will be easier.
We're going to use both.
Let's see if we can do a conservation of energy, and let's find out. Let's put it that way. All right, so what's given? We have an initial height, 5 meters. You know what? I'm just actually going to, the reality is, I can write all the givens and stuff like that. I'm actually, just for the sake of time, I'm going to jump to step 3. So, sure, we're solving for final velocity. I'll chuck that there. But the reality is, once you see this as a conservation of energy problem, you can write all your givens. That is useful. That's always useful. But for the sake of time, I'm honestly just going to jump to step 3. What energy do I start with equals what energy do I end with? That's really what it comes down to. When it comes conservation of energy problems, first, can you recognize it? And then can you set up that equation? If you can do those things, they're really easy problems. They're very straight. They all follow the same recipe. So, what energy do I start with? There's only 3 types of energy I've taught you. So it also makes it really easy. There's gravitational potential energy, there's elastic potential energy, and there's kinetic energy. There is technically way more types of energy than that in the world, but for our class, those are the only 3. So we just go through that checklist. Do I have elastic potential energy? Yes, I do. So I have some initial compression of the spring. Great. Do I have gravitational potential energy? I do. It's above ground. Do I have kinetic energy? No. No kinetic energy. It's not moving in the beginning. It's compressed on a spring. Can't imagine it's not moving. At the end, is the spring compressed anymore? No, it's done its thing. It's launched the thing. Nothing's compressing the spring anymore. Is it at above ground? Nope, don't have that either. What do I have? Kinetic energy. And then you just kind of, once you built the equation, it's just put the numbers and solve. So again, conservation of energy, can you set up the, I mean, you can make the argument all problems, can you set up the equation? But conservation of energy literally is, first you have to recognize it's that type of problem. Really straightforward. There's a beginning, there's an end, there's no collisions. And then you just go through your checklist. If you want, add that checklist to your note card. It's only 3 things, doesn't take up much room. We know K. There's my K, there's my height initial, and there's my X. Oh, and mass, we know mass as well. That's why I told you we need mass. Bam, plug and chug, easy peasy. You got everything you need. It's just math after that, nothing too bad. So, conservation of energy, great. This is one flavor of it. The other step to it, there's only one more thing I can do to make this more, I guess I can make this more complicated by having all the energies on both ends, whatever. The other thing I can do is I could add air resistance. Now, I have not taught you how to calculate air resistance, the energy lost to the air resistance. So what would that look like? So this is a conservation of energy problem with no air resistance. What would they look like to have the same problem? Yes, air resistance, which is totally not correct English. It's good enough. It gets the idea across. So what would it look like? It would look identical, but I'd change a couple things. I would still, maybe have the spring start here. Great. But here at the end, so it says if I compress a 10 kilogram box of spring 0.5 meters and the spring has a spring constant of 1,000 newtons per meter, how much energy was lost to friction? That's one way I could word this. Or I could say how much work was done by friction / air resistance. Both mean the exact same thing. If the final velocity is 2 meters per second.
How much energy was lost? Would that be a negative answer? And how much work was done? Would that be a positive answer?
They'll both be negative. Yeah, I say that. If I say how much energy was lost, I would accept a negative answer. Yeah, I would assume that you'd know that. Yeah, that's a good question. So if I said how much energy was lost, that is kind of ambiguous. I'll tell you I wouldn't be nitpicky with positives and negatives then, because it wouldn't be quite clear. Whereas work, I 100% need you to know whatever you calculate here better be negative. Because air resistance and friction in every problem I've given you does not cause things to speed up or slow down. It is technically, air resistance, friction, like both of those things cause you to lose energy to the environment. All right, so this problem, our setup is different. Not crazy different. Not crazy different. We are solving for work done by friction, so we'll put a little F there. And there's a couple ways So you have to remember, work is the energy gained or lost. Work is the energy gained or lost. So what does that look like? So on the equation sheet, I give you work equals change in energy. But ultimately, what does this boil down to? Work plus my initial energy equals my final energy. In this case, friction air resistance, I'm going to get a negative answer. I'm going to end, my final energy is going to have less than my initial energy. I'm hoping I picked a good number that works out that way. 2 meters per second is pretty slow. I tried to be pretty conservative here. But it's just the same thing. So work plus my spring, 1/2 kx initial squared, plus mgh initial equals 1/2 mv final squared. The equation is identical, but now I've got work involved. I just chucked a work on the left side and that's it. Because energy is gained or lost to the environment. Ideally, if I chose numbers correctly, this thing should be going faster than 2 meters per second. I didn't check in the last one, but I'm pretty confident it would be. This thing should be going faster than 2 meters per second. It's not. It's only going 2 meters per second. Where did my energy go? The air. Friction. The environment. I moved a bunch of air around and that box is flying through the air. Yeah.
And let's say you gave us mu.
Mm-hmm.
And
Oh, you wouldn't be able to. It would have to be on a flat surface. Yeah, this one, it would be impossible for you to calculate if I gave you mu, because I haven't taught you how to find the energy lost due to air resistance.
Okay.
Yeah, that's super complex. Yeah.
ask us about average force. Like average force of friction.
That one I wouldn't have you do either, because you would have to know the path it took, and that is a very complex thing to find. Finding the path that this thing took, because the air resistance would slow it down, which would change the path, disaster. The only time I could do anything like that is if something's sliding on the ground. Never through the air, because that's so complex. It's a good question though. Yeah.
If we were to set that up as like subtracting the work of friction from the final kinetic energy, would that be correct?
Sorry, what was it?
Like if we were to set this up as subtracting the
Oh, totally. Yeah, totally work. Yeah, it's all math. All works out the same.
okay.
Yeah, whether you had energy final minus energy initial equals work. Yep, totally fine. Yep. Math is math. Whether you do it in the beginning or the end with variables or with numbers, it should always work out. It's a good question. Yes, the question was, could I have left it as work equals energy final minus energy initial, just plug things in and call it a day? Yes. You totally, in which case you save yourself an algebra step. Okay, so conservation of energy. This is the 2 flavors of it. Conservation of energy, really important. At the end of the day, if you can do conservation energy, that means you can calculate kinetic energy. That means you can calculate all the different potential energies. So it kind of encapsulates almost all of energy. All right, the next big one is momentum. So, momentum. If things collide or if things split apart, it's a conservation momentum problem. Immediately, if things hit each other or they split apart, it's conservation energy or conservation momentum. Guaranteed. So, a rock is sitting still. Let's give it a mass. A 50 kilogram rock is sitting still. Suddenly, it blows up into 2 pieces. One of which is 30 kilograms and has a velocity vector of 3I minus 7J. What is the velocity? Let's make it spicy. What is the magnitude of velocity of the other piece? So, something started together and it blew up. Conservation momentum. Bam, immediately. And we draw a beautiful picture. There's a rock. And then one piece is going up, or no, going to the right and down. And you can predict which way the other piece is going to go. The other piece is going to go the other way. Some variety of that. So again, I'm going to skip step 1, write your givens. Totally recommend you do that. But for the sake of time today, write your givens. You should immediately recognize this is a conservation momentum. And so to that end, let's just kind of look at that. So we are solving for the magnitude of velocity of the other piece. We'll call it piece 2. Piece 1 is 1, piece 2 is 2. What a great decision. Conservation momentum, they start together. So we have mass. I guess we'll put mass 1, mass 2, sure. You could just call it the big mass of the whole thing. Times its initial velocity equals... Ooh, don't want to do that. I don't have much room on here, so I'm immediately going to tell you all. Remember, it's x and y, y'all. You have to do it in x and y. I was originally going to write it and then say it's x and y, but I want to save some space. So, the mass 1 plus mass 2 times the initial velocity in the x equals the mass 1 v1 final in the x plus mass 2 v2 final in the x. And then same thing, just replace all the x's with y's. Mass 1 plus mass 2 v initial y equals mass 1 v1 final y plus mass 2 v2 final y. We are very blessed, though, that this side is just 0, this side is just 0. The rock's not moving in the beginning. So this problem was actually mathematically pretty quick. It seems worse than it is, but mathematically this problem, once you set it up, you spend more time writing it than you do plugging in numbers. Yeah.
The magnitude is the hypotenuse, right?
Yep. Yeah, that was a great... So, I actually kind of write a little bit more here. So the question was, the magnitude is the hypotenuse, and that is correct. In fact, let me go... Oh, you cannot read that at all. Let me go ahead and put that over here, because this one was purposely a little mean. You have to remember that the magnitude of velocity, so the magnitude of velocity, the final velocity of it, is going to equal the square roots of the final velocity in the x squared plus the final velocity in the y squared. So you'll solve these two equations. They look worse than it is. Once you start putting in numbers, this whole side is 0. The left side of both sides is 0. Because the rock initially is not moving. And so that just equals mass 1 v1 fx. This one I'll plug in the numbers very quickly because it won't take me that long. I won't actually solve it, but I will at least plug in the numbers. So these problems look potentially intimidating at first. Again, this is a great free response kind of idea because it gets... Physics, it doesn't take that long. Most of the time is the physics. The math, very easy. So step 4, we take these two equations. So in the x, we get 0 equals 30 times 3 plus, and I didn't tell you the mass of the second piece, but I believe in your abilities. If the whole thing is 50 kilograms and one piece is 30 kilograms, the other piece has to be 20 kilograms. 20 plus 30 is 50. You do have to think through that. It's not given, but you can figure it out based on the information. If I said it broke into 2 pieces, I'm not going to be mean and say some of it got vaporized into dust. No. We're going to say it's a nice, clean break. That would be it would be impossible to solve if some of it vaporized. Momentum would still be conserved, but yeah, you can't really do it with the skills you all have. I wouldn't be able to do that. So there you go, super easy math there. And then the other one, and the y component, same thing. The left side 0, my rock ain't moving. 30 times -7 plus 20 times v2fy. Then you get those numbers, square root of those added together. Squares of those added together. So, this problem encapsulates, can you imagine what's going on? Can you set up a conservation momentum problem? Do you remember that you have to split into x and y? That's the key concepts here. Again, really most of this test is, do you know what energy is? Do you know what momentum is? Do you know what conservation of energy is? Do you know what conservation momentum is? That is most of it. That is, there's little bits and pieces here and there kind of tossed in. But for the most part, it's that. Do you know those things? There's, the oscillators and there's universal gravity, but most of the test is centered around energy and momentum. And kind of within energy is work, force and distance. All right. So, math-wise, that kind of gets you. So, what variations could I do on a momentum problem? I could make it an elastic collision instead. Two things hit each other. I would tell you one of the velocities of them after they bounce off. If I give you an elastic collision, I would not give you two unknowns. So I'll say two objects hit each other and bounce off each other. I give you both their initial velocities, I give you both their masses, I give you one of their final velocities finally. Okay, so make sure you all can do conservation of energy problems. Okay. Otherwise, let me give you all a ratio problem because I love ratio problems. And it's a skill that I think is very valuable. So, let's look at an equation. Which one do we want to do? Let's pick one we haven't looked at yet. All right, so let's see. A 500 kilogram. Let me think of what I'm going to give you all for this. A 500 kilogram car is traveling 30 meters per second and runs into the wall. How does the force on a person compare if the time for the collision is 0.5 seconds, so we'll call that F1, compared to 2.5 seconds, F2. All right, so again, this wording is not ideal. So I'll kind of explain this more in wording. Let's just say one case is your head hitting the steering wheel, one case is your head hitting an airbag. How does the force compare when it goes from 30 meters per second to nothing? So, whenever you all see a problem where it says, how does this compare to this? You immediately need to find the equation that relates the variables you have to the thing you want. So, what variables do I have and what do I want? Again, it is kind of like the Gibbons missing kind of thing. I have initial velocity, I have final velocity, I have mass, I have time, and I am curious about the force. That's how you look at these ratios. How does this compare to this? If this changes, what happens to this? You have to find the equation that relates those. If blank variable changes, how does other variable get affected? All an equation is the relationship between variables. If this changes, then this. That's all an equation does. That's why I like these problems. So I'll give you all a few moments, see if you can figure out what equation relates these things. What equation relates velocities and mass and time and force? Oh, just be there. Well, give me a few more moments and then, yeah, give it to me. I'll give him a few more moments to think about it. All right, which one is it? Yeah, so change in momentum, the way it'll be written on the formula sheet is FT, but you can, yep. So this is where you start. This is where the formula is. The change in momentum, you're like, I don't have momentum. Well, you do have to know that momentum is mv final minus mv initial. That is the change in momentum equals force times time. And then yes, the next step is isolate the variable that you're trying to find. So in this case, we're saying, what happens to the force? So you need to rearrange this problem in terms of F. F equals all the other crap. F equals all the other crap. Really simple in this case, just divide T over. So mv final minus mv initial over time. Now, you can straight up just calculate both of these. There's a couple ways you can go about that. I literally gave you all the numbers, so you can actually just straight up calculate the two and compare them. That's fine. So you could do that, that's fine. The nice thing is the final velocity is 0. So that's going to go away. The other way you could do this is you could recognize, if we call this one time 1 and we call this one time 2, we can recognize that time 2 is 5 times time 1. Time 2 is 5 times time 1. So if we just kind of put this here, the force is going to be negative mv initial over t. So this is my original one. We'll call this F1, so T1. F2 is going to be negative mv initial over T2, which we just said is 5T1. And if you pull that 5 out, you get that the force is 1/5. I'm going to put parentheses. If the time goes up, the force goes down. So one way I can get these problems is legitimate, just at the numbers. You can do the math and do it that way. The other way is I can say the time is 5 times bigger. What happens to the force? It's 1/5. Both versions I've kind of given you all. These basically boil down to, can you find the right equation? And do you know what happens if this changes? How does something else change? An extremely useful skill. You don't always want to have to put a calculator and do a bunch of... I didn't have to use a calculator for this. I didn't have to plug a calculator and do a bunch of math. It is a very useful skill in your day-to-day, like whatever career you kind of go into, that someone says, hey, if you change this thing, how is that going to affect this product? And to be able to say, oh, think about it for a little bit without needing a calculator, spend a bunch of time doing the calculation. Sometimes you have to do the calculation. Sometimes it's so complicated you have to. But the people that are really useful and impressive are someone that says, if this changes, how does this affect the product? They think a little bit, they say, oh, 5 times stronger, 5 times weaker, or we're going to need this much more concrete, or we're going to need to make it this much smaller. That's a really, having an understanding of if this changes, then how does this affect it? And when you can do that, you can check your work. That's another thing. After you've done all the math, does it make sense? And being able to do stuff like this helps you make sense of it. In this case, if the collision is longer, it makes sense that the force should be less. You're distributing that over a longer time. Again, you all know that airbags are safer than hitting a steering wheel. So it should make sense that making the collision last longer decreases the force. That's the cool thing with physics and engineering. It should all make sense. It's the world you live in. If it doesn't make sense, something is wrong. Either your understanding or your numbers or something is off. The world only works a certain way, whether you like it or not. Deterministic. All right. So let's see. Let's do another one like this. if I double the length of a pendulum, how does it affect the period? If I double the length of a pendulum, how does it affect the period? This is a good one. Kind of do it just algebraic. Same kind of idea. If this changes, how does something else change? So I'll give you all a few moments. Think about it. Try it out. And it boils down to, what information do I have? What's being affected? So if I double the length of it, let's see, can I put both of these up at the same time and actually be legible? There's a chance. All right. All right, there's all the formulas. Technically not all of them, but the one you need is on there, so that's good enough. If I double the length, again, it comes down to, can you find an equation that relates to them? And I've kind of made this, it's just one equation. These tend to be just one equation, one-step problems. Okay, I see that. Technically another step's in there. So, when it comes to a pendulum, there is an equation. There is no equation up there that relates period to length. What there is an equation that relates angular frequency to length. So, okay, I lied. This one does have two steps. So, WP, that is the angular frequency, is square root g over L. So we got length, g is gravity, 9.8. We're going to assume we're on Earth. And you say, but there's not period. Okay, can I go from angular frequency to period? And we look at our equation sheet. Oh, look. Angular frequency over 2 pi equals 1 over t. So you kind of rearrange this and you get t equals, well, I need to rearrange it for omega. Omega equals 2 pi over t. So there's a couple steps in this. So this is like the worst case scenario. But it's still the same exact thought process. Can I make an equation that relates one to the other? In this case, we just got to rearrange things to make it happen. So we then plug that in. Now I can go back to just full screen this. Make things a bit smaller so I have room again. So we just take that and plug it on in. So that goes right there. So 2 pi over t equals square root g over L. Do some algebra. If the thing you want is on the bottom, 1 over everything. Flip everything. So I'll let you all have a great time with this, but t is going to equal 1 over 2 pi square root of L over g. Did I mess it up? Flip it, multiply it over. Is it 2? Let me think through. Flip it. 2 pi's on the bottom. There you go. Yeah, thank you. Always better right step. So all I did, you know what? Let me show you all, because I made that mistake. It's good for me to show you. So I flip everything. Everything got inverse, so my t is up top. You're allowed to do that. I did 1 over both sides. And then you multiply the 2 pi over. All right. Great. So then the question, and now we're finally at the easy step. So this is the original. We had to build our equation. So my original period, we'll call it T naught, was just 2 pi L over G. My new period is 2 pi square root 2L over G. If I double the length, so I just doubled the length, and then I pull that to the front, which equals square root of 2 times 2 pi square root L over G. Long story short, what's my new period is square root of 2 times my original period. And that's very much crammed in there. I'll try to pretty it up some. So, again, this is like the worst case scenario, y'all. This is as bad as it gets in terms of these problems. But basically, can you play around with the equations? If this changes, how does it affect stuff? Can you rearrange the equations for the things you want? So, look through your old, so the quizzes, there's lots of examples where I've done these in the quizzes. If this changes, how does this get affected? There's lots of examples of these. Make sure you can do these. Otherwise, again, just make sure you can calculate can you calculate kinetic energy? Can you calculate momentum? Can you calculate potential energy? Just simple stuff like that. And yeah, same old, y'all. Go through the problems. Go through the ones you don't know how to do and set them up. If you're really unsure, work through the whole thing. Use your studying time well. This does not mean doing every single problem. It means doing the ones you don't know how to do. Look through the quizzes. If you look back at your quiz, you're like, I don't know how to do that one. Look through it. I'm going to post the solutions to the quiz I was did this last Saturday in the next 5 minutes. All your quiz solutions are kind of posted there, except for the one that's due this Saturday, because I can't post that because yada 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 yada. Don't forget about that. There is a quiz on gravity and so. Anyway, good luck, y'all. Study well, spend your time well. Spread out the studying. Send me emails. I will see you all Wednesday. Try to show up early so we can, because I will be here early, get things moving.